The impression I had was that I will present my talk after yours. So I'm going to skip a lot of steps, which you ought to have addressed.
If you want, I can spend 1 minute with you for what I was supposed to say. Let me know.
No, we didn't rehearse it. We will make it, it won't work.
No.
I know what I want to say.
Oh, okay.
But I don't know what you want to say.
Right. Let's stick to the scan. No problem.
Then I might as well stop.
Thank you.
Okay. Just getting the title, non-unitarily isotopic and Lie admissible scattering theories. The reason why I'm combining this talk is that my talk was split into 3 talks. One was repeated and one was omitted. And then I was to have talked this evening and in the morning again to continue with. So I might as well, with the time I'm given, do the, just go through, because the reason why anybody doesn't have to worry, what I'm going to say is already in this published volume. I'll give the references there. I have a CD of it, and it's on the flash. So if you're going to look for more details, I'll give them to you. Now I wish to introduce my younger colleague who's here with me, Sam Edago, who's with me. I'll present the paper tomorrow morning. Sam, could you stand to recognize? Well, I would say perhaps something very intriguing ahead of time. We found that the kinematics of hadronic mechanics is actually the kinematics they use for robotics. And it's very, very interesting. So our engineer's perspective is very important. These are my addresses. I'm University of Nigeria, but I also have run an NGO that enables me to do just what I want to do. Now, let's say the objective. This is the objective we agreed. I agree with Professor Santini. So I thought I should reproduce exactly as we said in our correspondence. And if you don't mind, I don't wish to be walking up and down.
I don't see the laser light.
The laser light. So that's a bad case. So
That's okay. Go ahead.
No, it's okay. It's necessary for the description of reversible synthesis of hadrons, such as that of the neutral pi meson and the neutron, because the synthesized masses is bigger than the sum of the original and final constituents, thus necessarily requiring a non-unitary scattering theory. Isomathematics is then necessary to achieve invariance and avoid the theorems of catastrophic inconsistencies. Now, from this perspective, it's not actually correct if you derived a theory with hadronic mechanics, then you fall back to conventional quantum mechanics. You already violate the theorem of catastrophic inconsistencies. Now, general scattering theory is necessary for the high energy scattering processes, since they are structurally irreversible over time. In particular, it is crucial to show that the very idea of interaction via exchange particle, while exact for the electromagnetic interactions, is no longer tenable for very high energy scattering. General mathematics is then needed to achieve invariance and avoid inconsistencies. Finally, it is crucial to indicate that the inclusion of irreversibility in scattering processes implies the lack of existence of the Higgs boson for many reasons, such as the isorenormalization of mass and so on. I've gone through that. Okay, the course outline are extracted exactly as in this book. It doesn't mean I'm going to reproduce every step, because where it involves mathematics, I'll leave it to Professor Santilli. Basic isotopic formulation, but the most crucial point in all this is how to avoid divergences in field theory. This is the idea, of course, came with the necessity in solid-state physics to avoid boundaries, to fold something into a torus. It has no boundary, and therefore no divergences. So from this point of view, I appreciate the fact that that can be achieved with a magnetic field, as the case may be. So we have identification of the iso unit, then elements of isoscattering theory, like the scattering amplitude, isoscattering metrics, isopropagators, convergence, isoexpansion, prediction of mini black holes. Then isotopies of Feynman graphs. This is actually the area that was of most interest to me. I've been working with Professor Santilli for many years. And one of the fortunes or misfortunes I may have had, that when I left Cavendish Lab at solid-state physics, I went to Stanford University, the Variant School. Then there was Robert Oakes, student of Feynman, who had visited Cambridge, and I decided to go as a postdoc to his classes and solve all the problems. So he says, give me any diagram whatsoever. I write the S matrix. It was so simple and so interesting. So the reference to this part of the work is available on the web, and hard copy is here. And I have a flash, and there's also a CD. Now, okay. Now the course outline continue reversible electron-proton and the electron-positron scattering processes. That will again involve introduction, review of formalism, but where I come in is where suddenly how to realize that kind of symmetry. And that symmetry, which I show, comes from the convective current in a medium. In fact, this is where the electron is getting its energy from convection from the ether. The reason why we don't call it neutrino is that neutrino has no rest mass. Otherwise, all the papers I've been writing since 1980-something was trying to account for the neutron, but I went into the problem that I named the same equation that I want to put electron and neutrino to go around the proton. Of course, Professor Santilli correctly told me, since the neutrino has no rest mass, it's an untenable model. And this was very, very helpful. So this is paper 4 of the series. There are 5 papers, and it took many years to construct. But I'll illustrate in a simple way. Okay, what I would have mentioned in this connection to bear in mind, apart from the dynamical symmetry, I explain in a way that I explain to my grandchildren when they come, say, Grandpa, what is it that you're doing? Then I have to tell them, say, what is hyperspace? What is genospace? Can I see it? I bring out my Brougham zone. I bring out my Brougham zone, which I've been carrying from many years, all the way from Drexel Institute of Technology. Then I say, when you put the cube inside, you have a genospace. And these two refer to two axes. That is, you are now using 6 dimensions instead of just 4. So you are departing from Minkowski space already. You find that this double knot axis was used in modeling goat or seashells and so on. But we come to that. Then, of course, one other thing we learned from solid-state physics is that the whole universe, how does the universe from the microscopic to the macroscopic sustain and manage energy? It has 2 structures that have the same packing fraction. It can either be a cube or a face center cubic. They have the same packing fraction. So when they're unable to distribute the energy uniformly, it prefers to go hexagonal. So this is how I explain, that's why trees grow up. Of course, they broaden, but they grow more up than sideways because that's the direction light is coming and the energy is coming. This is for 11-year-old children, but that's the way I see it. Now, so I say paper 4 of the series contains all this. Something is lost. So computation, before we give just cursory, representation of ISO, going from conventional Coulomb scattering to the profile electron-proton ISO scattering and the experimental verification, I will did this change? Okay. Now, as I said, this will have come tomorrow, but I might as well mention it because we have a series of 5 papers. This is the theory of the irreversible process will require introduction of isodual of matter and antimatter. Scientifically admissible genomathematics, geno-units products, and so on, geno-function analysis. This is almost all mathematics. And I should mention my first degree was in mathematics. And when I went to Cambridge from Nigeria, I was in the Department of Applied Mathematics and Theoretical Physics, the solid-state division. And they don't make any differentiation between mathematics and physics. In fact, they call it natural philosophy. I found it very attractive nomenclature. So I can learn from a mystic. I can learn from anybody whatsoever that has any idea on that natural philosophy, and then put them in mathematical form. So, okay, so the continuation of that, the elements of the admissible, this again will be handled by Professor Santilli. You come to genotopy of Dirac-Santilli ISO equation. I was complaining that if you're working at very high energy, then you should use relativistic theory. So using non-relativistic theory at high energy to describe processes going on at temperatures of, millions of degrees, to me may activate, I'm not saying, it's clear, it may activate some inconsistencies. Now, invariant genotopy of theory, fundamentally admissible scattering theory, review, and genotopy of the ISO scattering formalism. But this is where we got what they normally call the standard model. It's an SU3 by U1. Then they put 031. But I'm putting 042. Can go forward in time. And the idea is this. When you add the dimensions, you get 4 plus 6 is equal to 10. There are 10-dimensional theories. There are other high dimensions. But this cube hexagon hyperspace I'm talking about says that the structure relevant is actually 6 plus 4 equal to 10, not 5 plus 5. The reason I'll give tomorrow is that rotational symmetry through 5 is not permitted in 3-dimensional space. And what nature does, nature is very silent. When you do something wrong, it's not going to come with a bang. on you, it will quietly take its toll. And that is the source of death of many theories and civilizations. So I'll give the applications to deep inelastic scattering, experimental results, describe the structure functions, concluding remarks. Actually, if I would acknowledge, I work with a large number of students, some of them undergraduate, some we come with very unusual skill. Maybe you were born in a house that has computer from childhood. And you say, no, Daddy, don't do it this way, do it this way. And I find it to be very, very rejuvenating. So to summarize our introductory remarks, according to Professor Santilli, the protracted lack of resolution of fundamental problems in science signals the need for basically new mathematics. And he gives example, the case of biological structures, grand unification, irreversibility at the classical and operative levels, hadronic constituents definable in our space-time, classical representation of antimatter. Then he said, and other problems have shown that each of the above open problems admits basically novel resolution if a new mathematics specifically conceived for the task at hand is built. I have moreover shown that no new mathematics is actually possible without new numbers. The new mathematics envisaged by Santilli is called isomathematics for reversible processes, genomathematics for irreversible processes, and hypermathematics for hyperstructures such as quasicrystals and DNA. I'll address the issue of quasicrystals tomorrow. Well, this slide was produced by my technical assistant who said that it's more graphic if I rotate it so that people will pay attention. So basically, you have, this is the structure of the theory we're talking about. From isonumbers to isofields, isospaces, isorepresentation, we come to isotopy branch. Lie isotopy branch of hadronic mechanics. From genonumbers to genofields, you come to Lie admissible branch of hadronic mechanics. Let's see what you did there. Okay. Just for emphasis. Okay, we made two assumptions. Remember, what is our objective? The first critical assumption is that particles are non-point-like. Once a particle is non-point-like, you allow geometry comes in automatically. If it's a sphere, I can put anything I like inside the sphere. Or I can deform the sphere into a torus, and or into hyperspace. So the important point is that within this, when you are discussing, say, the neutron production from isoproduction with proton electron scattering, you're going to have an area where quantum mechanics, okay, it doesn't show that. Quantum mechanics goes everywhere, except in this region. So a schematic view of the main assumptions of the Lie isotopic scattering theory, namely the validity of conventional quantum mechanics everywhere in exterior condition, and the validity of the covering hadronic mechanics for the interior conditions characterized by a spherical region or typical size 10 to minus 3. That was the state of hadronic mechanics before I joined the foray. Of course, one of the demonstrations, experimental motivations, normally before you do any theory, there's experimental motivation, but theory is an art. Then my first degree in mathematics was BA in arts. It doesn't have to be, everything artistic doesn't have to be scientific. So, but when you go to science, there are more than experimental motivation, and this is one of them. The ISO or bending of light in this curve, which you can easily observe. If you take a laser light, pour light in a glass, and it doesn't require sophisticated equipment just to demonstrate. Now, this is the generalization that we had in mind, or we eventually agreed upon. We go from point particles to where everywhere is quantum mechanics, to non-point like spherical particle, then deformation of the sphere into torus. That's, of course, a topological problem. Then, this is what I was trying to, the graph I was trying to show where you inscribe this inside that actually what is, normally you think this is the Brougham zone inscribed in a cube. But the point is the reciprocity between phase center and cubic center lattice do emerge in this kind of theory, and you have what is called hyperspace or genospace. This is what I was demonstrating there. Okay, now tomorrow we've done more elaboration of that. So this is what we had before. Now I put more structure to show. I got this from the pictures of you find in the Santilli Foundation about the time machine and all that. But what we have is here. It's particle, anti-particle. That's why I present them this way. There's a complete symmetry. And this is why I was concerned when I was saying, if we go to thermodynamics, reversible or irreversible, what happens to other properties like time reversal? I've shown this before. Now, this is solid-state physics, 10 to minus 8 here. And when you go to solid-state physics, the new insight that comes that you don't have to worry only about the frequency, which is where the iso ray shift comes about. You worry about deformation of the lattice from other sphere into or quantization of the space inside. You find that this leads to actually quantum theory of gravity. The quantization occurs in here. And the restriction we have, the reason why I will change this, why I will not agree with this, it has hexagon, all right, cube, hexagon, basic symmetry. But then they also include the pentagon. And I say a pentagon is not allowed symmetry in three-dimensional space from if you want to have periodicity. And this is perhaps why quasi-crystals were not discovered, because nature destroys it. Anytime you have 5 dimensions, nature destroys it slowly, over thousands of years, or millions. So we move on. Now, the second assumption we're going to make, which is contingent on the first one, namely, how do you actually mathematically implement this non-unitary situation? The Dirac delta function. The singularities arise because of presence of Dirac delta function. In fact, if you normally, the way one will deal with it is that 1 upon r, to avoid divergence, you have to put plus I epsilon below. R plus I epsilon. Then you expand it. It's principal value, or 1 upon r plus delta function. And that delta function represents contact interaction. And I think that is the critical thing missing in physics. And one of my students have worked out, we would want to do energy band in a gravitational field, including contact interaction. It will involve the normalization of mass and all that. But what we have here is Dirac muing mu Santilli iso-Dirac delta function. So it has this hat here. The ISO unit, well, you define with all these, you have to, lift it, which typically involves this ISO unit. And then here, you have to sum over k from 1 to n. Now we'll find tomorrow that is this summation over from 1 to n that brings in the issue of whether you're folding the system to whether to preserve translational periodicity or you're not. Anything that if you fold, if you go to a symmetry other than the conventional one, you break that symmetry of that control Bragg's law or reflection. As I say, tomorrow will be a day for that. So 2 assumptions. This broadening of the delta function enables us to achieve the convergence we are after in scattering theory. So anywhere we have divergence, delta function, we replace it by the Dirac mu Santilli iso delta function. Okay, so we go back again to the problem at hand, namely, we want to discuss reversible processes, neutral pion and neutron synthesis. These are the processes we have in mind. 2 electrons will annihilate into that, and it's a reversible process. And you have proton and the electron give you neutron plus nu, and you have this. So the problems are some of the rest masses, that's very important. Or the constraints, electron and positron, are less than the neutral pion rest mass. Some of the rest masses of the constitutional, or the constraints, electron and proton, are less than the neutron mass. Now, when you talk of rest mass, you're automatically invoking relativistic energy momentum relation. Now, this is contrary to conventional quantum mechanical characterization of bound states with negative binding energy. So this is the problem we're trying to solve. I'm looking at my time, so okay. Now, this is for those people who in field theory, this is the way to conceptualize the problem we're trying to, or the situation we're trying to represent physically. This is electron point annihilation to 2 photons. This is electron-positron scattering with exchange of gamma ray. Well, what happens when they overlap? Is that overlap we're trying to describe and say, you see a conventional Feynman graph for that, annihilation to 2 photons, then this is Coulomb scattering via virtual exchange of photon. That's the way Diamond represents Coulomb interaction. And see non-unitary image of non-Hamiltonian interactions of extended wave packets due to the overlapping in the annihilation process in A, or the model of diffusion process in this. So it's very clear what change we're trying to introduce. So this may not be precise, but this is just to give you an idea of the kind of regimes we're trying to bring together. Take this process, very well known in current algebra and all that, some rules. We say mere isotopic branch. We'll explain this. To explain this, you're going to go to Lie admissible branch. I wonder if Professor Santilli is do you have any basic objection to that? Okay, so what changes, what do we achieve? Because after all the hula bala about whatever we do, we have to be able to put it in the language that people will understand. So this is quantum electrodynamics, and this is hadronic mechanics. So what have we done? This is first quantization, Coulomb vertex. This is the Coulomb, how you represent it in the book by Bujokin and Drell. It has this 1 upon x. The divergence is coming from here. Now, when we go to hadronic mechanics, we replace that by Yukawa vertex. In other words, the electromagnetic interaction goes into strong interaction. That is the crux of the matter. That's a level of first quantization. Then at level of second quantization, you can have electron-positron emission of it. That's the interaction C dagger CQ, or you can have the dual, where you reverse the mesons and the fermions. So you have this process and that. Spin mutation. So we can see the how and where the new features in hadronic mechanics come from point of view of Feynman graph, or generalized Feynman graph. Okay, so let's see how you represent it. The representation is already available, has been available in Santilli Foundation for years, and I always carry them along. Positron. If you have 2-point particles, you have atomic level, that this will be moving as point with respect to that. So you have positronium energy levels. This is atomic mechanics. Then here is something, now when you compress it, they come here, they form a neutron. This is a typical way of representing the product. That's a change in topology. That is very important. Now, I'll try to generalize, this representation by McCullough. I can't read that now, because I've not met the man before, but I know the work. So what are we talking about? If electron is non-point-like, it will form a ring, a torus, round a point-like, a non-point-like proton. So this is very easy to perceive, and therefore what you get when this happens is you get the neutron. The mathematics, where I know by 1980s or shortly after Santilli had circulated his invention, and I had to continue to maintain my interaction with people overseas because we're dealing with very chaotic conditions in Nigeria. And I found an ISO unit, and ISO mathematics is the way to handle it. So this split level is the neutron and is the. But whether you're going to get it by solving a conventional eigenvalue problem, well, technically, if you take a Yukawa potential and solve the problem, you may be able to generate it by dealing with the parameters, the mass and the charge. But there's issue of consistency down the line. This is why what Professor Santilli has always hammered into my head. And this is why I was interested in the torus first place. So scattering, this is an example of irreversible process. It looks irreversible there, and we describe this process, or we say electron plus the dual with that proton. This is intended to capture both Stanford University and sand, the kind of experiment they're doing. Then you have this deep inelastic scattering. We're going to deal with the three. Let's spin it around. Okay, now, I'm just about to introduce the idea of more general space. Then, this is a hexagon that I inscribed inside a cube. Then, the red axis are of charge and lepton number, and baryon number to represent all elementary particles. Then you have the other axis is lepton number. Okay, one is isotopic spin, why the black ones. The other one is, since they are orthogonal, we have to assume that they can be represented in one space, but they are rotated. That is where the six-dimensional space is coming from. That's it. This is the growing seashell in six-dimensional space. The doubling of the axis is what I've captured here. And what is this rotation? Is what is known as the Cabibbo rotation. So now I'm going to, this is not part of our paper, but because of the shortness of time, I'm going to just say if I had proton, that is, I was interested in superconductivity in neutron star. Then I say if they change that particle, then they can attract. We're using this as a trigger. So you can understand isosuperconductivity of proton in neutron star. But at the same time, you can understand isosuperconductivity of electrons in neutron star. And the two coexist. So how do you understand that? We have to go to Geno scattering theory. So what I've done is this. I put them together this way. Then if you're still interested in point light particles, you can go here. Does that ring a bell when you talk about the, I'm hearing you, of course. I'm not following everything going on, but this tetrahedron is very important in many of these processes because at the high energy you're trying to create a neutron. As happens in stars, say a neutron star, you can have proton superconductivity as well as electron superconductivity. And this is described as Geno superconductivity. And it just comes out very simply forming that kind of object. I represented it again here. Represent a proton Cooper pair correlated with electron pair trigger. So this one now acts as a trigger for that in the Rutherford-Santilli hadronic mechanics model. And you see this Cooper pair, not charge and parity. So you put this in here, what do you get? It's approximately helium. And I went further. Excuse me, I was just, this will happen to be part of my thinking. I've not thrown away, I mean, since I had that three-dimensional thing, I could say what actually happens in the universe may well be that it's a hydrogen, anti-hydrogen. You can see in the graph we showed hydrogen is an elementary particle from that diagram, cube hexagon. And therefore, you can talk of hydrogen, anti-hydrogen annihilation. If you're quark-oriented, you can make two tetrahedra out of it. Or you can make it into one tetrahedron. But what do you get? You get a vortex. Okay, now I'll I've done 17, 18. I'll soon be through. The rest are mathematics. So how to introduce this dynamical symmetry? You have to lift Dirac current. You lift it, but you add the current due to the vortex. That's the convective current, which gives the electron the magnetic moment, the anomalous magnetic moment. Is introduced at fundamental level in this model. Then, if you're of Lagrangian school of thought, if you write it, you lift everything. This is the conventional Dirac, Lagrangian lifted, but you're going to add in the vortex, the convective current. And it leads to the what Beirut. Actually, this is where I entered high energy physics. I was asked to teach high energy physics in Rolla, Missouri. They said, you're going to Stanford, you know it better than we do. So I wrote to Dirac, who was my teacher at Cambridge. I said, I want to change your gamma matrices to be position dependent so I can describe gravity. He wrote back, I'm still looking for that letter, and said he believes that gravity is a many particle theory. It's an exact quotation. So fiddling with one particle theory will not solve the problem. So let's see how this thing works out in practice. A summary, how you apply it to neutron production. So the schema is this. Quantum mechanics has O31 symmetry. We elevate this in conventional theory to O42. That will be Beirut's kind of approach. Or you go to hadronic mechanics and you go to ISO 42 symmetry. Now, how does it work out? You can deal with these two processes, proton, electron going to neutron plus neutral particle, or this. In one case, you're going to put a particle here. As if you want to retain the spin statistics theorem. This is conventional quantum mechanics. And you can treat the proton as a point particle. So to some extent, you're justified in doing that. Then, but now when you go to hadronic mechanics, there are only two. Therefore, the isoelectron must be a covering of the electron with the etheron. Now, when you go to this process, we again find that when we make the same replacement we did here, we'll get this equation gets lifted to this. And this equation we've talked about. Then, of course, mathematically, we're going from point interaction to a situation where you have, if you have W, there are the electron and the proton, and then non-like point particles, and they overlap. This has to move faster. But I can stop anywhere. I'm out of time. Okay, this is the way it works out mathematically. So let us say, what is the limit of the atomic limit of this theory? You find that this equation, where you include the convective current, the vortex current, we give you that. And the equation I asked Dirac is that I don't want to put mass by hand into your equation. I want mass to appear as eigenvalue. And I can do that only if I add the vortex term. So you now have two masses coming out of this, the quadratic equation. This is ubiquitous equals 7. You have this 1.65 for positive and negative. Then the mass difference of 1.53 mass of electron. You see indeed that the mass difference of the neutron from that of proton and the electron and the etherino is negative. So that conceptually, we can understand what we've done from quantum mechanics. But this is only a limiting case, a non-trivial limiting case of the theory. Now, in terms of Gelman matrices, in terms of SU3, I show that this is exactly equivalent to putting this here and that there, so that what I basically have is this will give you diagonal, that is, this will be half. Everything now works out mathematically, so that there's a justification. In other words, this theory tends to the appropriate limit where we want it to tend to. Okay, now I repeated what I've just said before, and now I put them in terms of diagram. This is the long-range interaction. This is where only the proton is non-point-like. You see how this. But this is where both the proton and the electron are non-point-like. You have the overlap. Okay, now because I have interest in projective geometry, Dirac developed spinor theory from projective geometry because his lecturer was Professor Todd of Department of Mathematics, and I went to his lectures, and you see you can construct spinors. They correspond to a tangential envelope of, you can use the envelope to describe a curve. And this is what you get. But now I'm interested in spherical deformation. And you can see you can combine both Pappus' theorem or Charles' theorem. If you have a hexagon, the cross joints will be concurrent, and the tangents will be linear. That's a very ancient theorem. And of course, it's all in the text. You can now work it out mathematically. But what is very interesting is that I have to lift the third component of spin, this quantity, which is the iso unit. Which is used the modification of the unit used by Dirac. But this was way back, and Santilli eventually argued that the iso unit must be positive definite. Just to drive matters home, because basically I find that many physicists think two-dimensional. So it's not easy to visualize things in 3 dimensions. So they always make R, x squared plus y squared plus z, and they wash out every detail. So you can see that from this, if I take this section there and project them here, I have it just as if you have a particle and a hole here, or something that's whirling around with the electron that has 0 mass. So it's not neutrino, it's the heterino. And you can see the cube hexagon system. And I'll show how contact interaction leads to this. I'm not sure I'll be able to do that tomorrow because it requires working overnight on the view graphs, but I won't do that. Okay, then you go to the 4-dimensional analog. For the elaboration of ellipsoidal deformation gives you this Minkowski space. But what is interesting here, this is not symmetric. You can see this is -1, 1. So it does have both something that relates to gravity and anti-symmetric part that relates to electric field. The rest are mathematics. Okay, this is a continuation. Actually, what Dirac showed was that one set of the 4 matrices we described spin-half particles. The other one described integral spin particle with linear equation. And because of my interest in geometry, What this does, actually, this is a non-symmetric part. It brings in this term. And I should mention, I work with Professor Gill of Howard University to say what are the consequences of this. This one in parametric equation of a torus. So it's a corresponds to a deformation, mathematically. Okay, I have roughly. Okay, I'll quickly go through these. Okay, these are the diagrams. Computation of the iso asymmetry from Feynman graphs. That's it. What I liked Robert Oakes in Stanford was say, give me any diagram whatsoever. I write the asymmetries for you. So this is how I wrote down these asymmetries. But you follow closely because of isosymmetry. You follow the conventional thing. And what you want to ensure is that at the end of the day, you'll be able to account for those characteristics I was talking about, namely when the electron penetrates inside. In other words, after that longish calculation, you come to asymmetries of this form, then you do make a transform into currents. You have modular potential. So it becomes interaction of currents. And tomorrow, I show that the currents, which is the source of current algebra, correspond to representing the tetrahedron by the plane.
5 minutes.
5 minutes, that's a long time. So once you have that, you can do the scattering cross-section using the standard formula. This is wasting our time, but these are the bits of the arguments. Okay, this is what you get for EP scattering generalized. You can see the new generalization consists in changing this theory. Remember earlier on, I've said how the vertex is changed. Change that. All these are lifted and be able to account for. When the red arrow tells you how to write down the S-matrix, you start from the left, put down everything. Okay, I won't spend much time on this again. The same process. Okay, deep inelastic scattering. I won't go into more details of this because we require developing GNO mathematics. But tomorrow, I'll develop it from a slightly the part that relates to GNO scattering theory of solid-state physics. So to come to the same thing, I hope Professor Santilli will elaborate on that. But we've used this theory to fit the experiments. Actually, the issues that we're dealing with two kinds of curve. It's a population inversion kind of curve. One curve is going exponential, the other one is decaying. When you add the two of them, you get that. This is the Riccati equation, solution of Riccati equation, which is a source of the admissible algebra. Same thing continued, same thing. Thank you, and thank you for attention.
Thank you very much. Ladies and gentlemen, Professor Santilli will complement this presentation. Thank you.
Professor Animalu, it's always a pleasure to hear your beautiful, diversified lectures. I was supposed to talk before you, but I want you to talk before me. But basically, I have only very few comments. We are all tired. This lecture, just I want to say that the scattering component of Professor Animalu lecture refers to 5 papers that we worked out together after lots of work, as he said. Those papers were the essence of the Nepal conference in January 2011, dedicated to admissible algebra, and Professor Animalu and I will very likely this is over 200 pages plus additional work. Very likely we will have a joint monograph, very likely published by Springer or some other publisher, and we will keep you informed. I have only a few comments I would like to make. Some have been asked, a couple of minutes, no more. Feynman diagram. At the time they were discovered, they were magnificent. There was no other alternative. However, with the advancement of the knowledge and the admission that there exists no point-like wave packet, there exists point-like charges, but there exists no point-like wave packet, they became the limitation came to emerge. Perhaps the biggest limitation that I know of Feynman diagrams is related to the divergences. I cannot accept as final a scattering theory that contains infinities. Because with infinity, let's be honest with each other. If there are infinities, I know many ways to subtract them, and therefore I get any number I want out of it. So the moment you admit that particles have an extended wave packet, you activate the hadronic mechanics, and automatically you avoid all divergences. They are eliminated by conception. Professor Animalu very brilliantly indicated that first conceptually and then technically presented to you this point. I believe just elimination, the automatic, assured elimination. In this case, Professor Kai Wei is the isotopic element has to have a small numerical value in absolute value, the isotopic element. In other cases, no. But in this case, to avoid divergency, the isotopic element has to be small. But not in other cases, so your comment is correct. Another couple of more comments. So just the elimination of divergences should allow some serious consideration of this work. But there is more. Professor Animalu has brilliantly indicated the reversible reaction, the synthesis of the pi and the synthesis of the nu. I just want to add one point, namely because the objection, to prevent an objection, namely that since we are talking about scattering, then not necessarily the energy is missing. That's the objection I have heard. Not to you, not to your talk, Professor Animalu. We work this together. So, no, let me clarify this, because you can have an electron and positron at very high energy. Of course, you synthesize the pi zero. The misleading point is this, that it creates manipulation, is that when the two electrons have about 100, you need 134 MeV to synthesize the pi zero. When the electrons and the positron have a relative energy, kinetic energy of 134 MeV, the cross-section is virtually zero. It's 10 to the minus 50 bars or something enormously small. Professor Animalu, no, please. No, I cannot allow this. Please, no. Besides, you will have patience very soon. No, please, come here.
I'm an old man, I'm resting a little.
Oh, okay, that's different. Okay, if you want to rest, yes. Okay.
Let me rest a little bit and respond.
Okay, that's different.
I have to have lunch today to make sure I understand this.
But this work together. I will not allow you me alone. Never. Please don't leave me alone. So the insidious point that when you have this high energy, the electron, there is no possibility that they synthesize, because the cross section is absolutely zero. Exactly the same for the electron and the proton. When the kinetic energy is 1 MeV, the cross section 10 to minus 20 bar. So there is no possibility they will synthesize. So this is our point, that the synthesis of the representation of the scattering of the electron and positron into the synthesis of the pi and then the decay require necessarily a non-unitary scattering theory. It is necessary to the best of my, I've been unable to represent that synthesis in a scattering theory with a unitary. I just couldn't. One final point, and then we should, because we are all tired, I would like to remind that scattering, non-unitary scattering theory has been proposed since, the need for non-Hamiltonian interactions has been identified. We are not the first. Our contribution, and there have been lots of non-unitary theory that have been worked out. Our contribution is the following. Whenever you have a non-unitary scattering matrix, then it has been proved that it violates causality. And this is the historical reason why non-unitary scattering theory were abandoned. And here is again the importance of isomathematics, because it allows the reconstruction of a fully causal description. One final point, allow me a little touch of politics. The touch of politics is Professor Animalu, very technically, this is the truth, it's not laudation, Professor Animalu, the truth is the truth. Very, very technically and very, very, very nicely indicated, first conceptually and then with the equations, that the Higgs boson cannot exist as presented. For many reasons. First of all, because when you admit that the particles have a extended wave packet, not charge, wave packet, you have an automatic renormalization of the mass, which is unavoidable. So to begin with, the mass of the Higgs is pure theology by the authors of what they say. But that's only the beginning. And then when you go at this extremely high region and you examine the diagrams that Professor Animalu so nicely presented, there is no possibility of representing interaction via an exchange of a particle. In other words, you start with Feynman, quantum electrodynamics, scattering, Coulomb scattering of electrons and proton. Yes, then you can represent correctly and beautifully the interaction by the exchange of a particle. But when you go up and you reach a point in which the exchange of a particle is causes inconsistency. Professor Animalu, again, very beautiful, because the truth presented to you the interaction of an electron and the positron. And if you mediated with the photon, you violated the iso self-duality. In other words, why you selected the photon? Because then why about using the iso-dual photon? You cannot. Why you selected one and not the other? You dig there deep inside, and you have to violate the democracy between matter and antimatter. The conclusion is that when an electron and a positron, the wave packet overlap, the annihilation starts without any exchange. This is beautifully presented by Professor Animalu in those diagrams with the overlapping of, in other words, he presented first the Feynman representation of the annihilation proton, and then the one by hadronic mechanics, and I want to compliment him. One final political point: why my former colleagues at Harvard and MIT, they are absolutely attached to quarks as physical particles. They're attached to this, and then the moment you present alternative, you see their nostrils, they vibrate like a horse. It is true. They become so irate at you that they look at you with hatred. You can cut the hatred with the knife. Why so? For one reason, because quarks are point-like. If you hear Lederman, former director of Fermilab, every time he thinks about quarks, he says point-like quarks, point-like quarks. Weinberg and many other people have always insist on point-like quarks. Why? For a political reason, pure 100% politics. Those are smart guys. Those are not very, very intelligent person. But they are politicians, unfortunately. Because only by reducing the scattering region to point particle, they can justify the use of relativistic scattering mechanics and the validity of Einstein relativity inside the scattering region. The moment you admit that a quark can have a wave packet which is extended, all that construction collapses. And then you end in a covering. You end up necessarily in a covering theory. One final point. I believe, of course, when you look at the acceleration during the acceleration phase, Einstein's special relativity is valid, verified every day. I have nothing to say. But at the moment it leaves the acceleration, and you have this inelastic scattering. Ladies and gentlemen, I cannot accept Einstein's special relativity in an irreversible process. And at that moment, the admissible covering is the only invariant formulation that I know as a covering. So I have no word to recommend to give us some help, because we work very, very hard. But we need help and to keep pushing this theory forward. Thank you very much. Compliments goes to him, because he's a big speaker.
Okay. Any questions,
Any
please?
question before we run away? Any criticism?
Comments?
We are all tired. We are tired.
So, Professor Animalu, thank you very much for a beautiful presentation. And I have few questions, but I ask only one. It is there is a problem of divergences in the quantum electrodynamics, you know, and these divergences the reason of these divergences are very well known. The reason is that gauge symmetry is has an infinite volume. So when you integrate out, you have a divergency. So this is a very simple case. Quantum electrodynamics is a very simple case of quantum gauge field theories. And I see no problem in quantum electrodynamics with divergences because at the very early stage, it was indeed a problem for people to understand how to handle this. They used dimensional regularization, they used another method, second, third method, but after all, it was invented the BRST quantization, which means, which is an abbreviation from Becquerel-Astora-Tutin approach. I have a paper on this, and which shows very quickly that all divergences are here, and we can handle it very easily by using not the usual quantization, but BRST quantization method. So I have no any problem with divergences at the moment. So.
Please. Of course, I want to hear you too. No, the quantum electrodynamic has been verified to be valid up to, we don't criticize quantum electrodynamics. No, our point is that this magnificent theory, that's so beautiful in that framework that you refer, is being pushed all the way to high energy scattering. This is when you go to high energy scattering, then the question of the divergence is completely different. And at that moment becomes, I know how to modify, everything you say, I know how to modify it and get any number, the infinities are not that easy removable. So please, no, I don't criticize quantum electrodynamics, and at least me. Please express your view.
Now the elaboration I'll make is that if you're working in a projective space, infinity is not allowed in 3 places of your coordinate because it's not defined. This is why Dirac was always opposing it. Because in unitary space, or projective unitary space, all that's important, the ratio of the coordinates is automatically scale invariant. And therefore, if you have 0 to 0 to 0, it's meaningless. And that's why you have to go to 4 dimensions. In fact, Dirac said that in his memoir, that he found it easy to work with projective geometry because can visualize 3-dimensional space as 4-dimensional projective space. So no infinities.
I met Paul Dirac before his death I met Paul Dirac before, I think I mentioned before his death in 1980 in Florida, and he strongly was against divergences, that the theory has to come without any divergence. He recommended a covering theory, not necessarily for quantum electrodynamics, but in general.
One more
A question, please. Professor Animalu, thank you very much for your talking. Do you think that it works to generate this admissible theory into hyperstructures?
Yes.
Because we have a plan.
Yes.
It works to.
I put more structures in here.
Okay. Thank you. Thank you.
Maybe elaborate on this point because we are doing a research. Yes, Professor Vogioclis. If you consider an elementary non-irreversible reaction, then you can do it with a single-valued Lie admissible theory. But the moment you end up with a very large variety of, a cascade of particle production, the multi-valued formulation of Lie admissible formulation of the scattering theory is unavoidable.
Professor Santilli forgot another important political position to this kind of science. The quarks are also considered by hot pseudoscientists like done by strings. This is another riddle because you make opponents like Gabriele Veneziano, Edward Wheaton, and in my personal opinion, string theory is pure rubbish.
Thank you. This is string, what vibrates? Nothing. If you ask what is vibrating, nothing. They don't know what is vibrating.
Animalu, I have a question. So, first, I like your presentation. It's very elegant. And I know the nuclear, right? The mass distribution may not be the same like the charge distribution. So when you say two nuclei overlap, right? So when you think the mass distribution is the same like the charge distribution or something?
Mass distribution, as I said, is what I'm working on now. When you have only negative character. Then you can still write your 1 upon r plus I epsilon is 1 upon principal value plus delta. Then if you fold the whole thing up and allow only 5 kinds of rotational symmetry, that's linear quantization, all your final structure concept will come out. No, anything.
Thank you.
What I will say is that I work with different kinds of
But I showed you that.
the linguists, for example, Jewish origin, they don't have vowels. So they have to permute 5 degrees of freedom. Vowels around that in the, it's what we call Kabbalah. So, and what is, if I give you, say, we have 3 words, Eke is snake, Eke is create, Eke is 4-day week. What am I doing? Just unitary transformation of the word K in linguistics. It's unitary. It may not be unitary, because in one case, I listened to boys challenge in morning, and I said, this have vowels in their language. How did language even originate? What did a child that came up and learned how to say mom? That's the first word. But what is mom? There's one vowel between 2 consonants. And I can now put more unitary transformation. This is where I show where hypermathematics is going to come. I have something in my language that says, yes, let's put it through this. It has to do with 4. What's called the magic square. I'll talk about it. I didn't turn it tomorrow because it's still
I have informal, so it's just informal.